So
If you started, I start recording.
all right, so this presentation is about analog circuit design in BCD technology. BCD means bipolar, CMOS, and DMOS. So in this presentation, I'm gonna explain these three terms. So CMOS is consisted of NMOS and PMOS, and then we're gonna see what BJT means, bipolar junction transistor, and finally we're gonna see what DMOS is about. So let's start with NMOS, PMOS, and CMOS. So firstly, NMOS, which is N-type metal oxide semiconductor. So this consists of highly doped N type regions, which is denoted by N plus, as we can see right here, and they are situated in a P well. So this part is moderately doped p-type doped, and then these two highly doped n-type regions, they are source and drain, and either can be source or drain. And then so the region between these two source and drain is called the channel region, and there is a thin layer of silicon dioxide above this channel region. So and then above that silicon dioxide layer is a metal gate. So that's why it is called metal oxide semiconductor, because there's semiconductor, there's oxide there's oxide above, and then there's metal. Metal. So how does NMOS works? So as we can see right here, that there is a NPN junction. There are two PN junctions right here. So because there is PN junction, there will be some natural depletion region. So as we can see right here, this is called cutoff region. And if we apply a positive voltage in the gate, then as the well is p-type, there are more holes. The hole concentration is greater, so the holes will be repelled, and as a result, the depletion region will be extended, as we can see in this picture. Not only the depletion region will be extended, but also there will be an inversion layer that will be created as we increase the gate voltage, as we can see right here. So basically, this part is becoming an N-type. And once the gate voltage exceeds a certain threshold, the source and drain will be connected with this N-type new type of substrate, and there will be an electron flow from the drain to the source. And that's how the NMOS works. PMOS is basically the exact opposite of NMOS. So it works pretty same way, but here we have highly doped P regions in N well, and that's the only difference. Now CMOS is basically combining NMOS and PMOS in a P substrate. So this is a symmetrical device. So that means the source and the drain can be interchangeable, and this can be shared by multiple devices. And the PN junctions are sorted and reverse biased. CMOS stands for complementary metal oxide semiconductor. So the bipolar parasitics for CMOS is latch-up, as we can see right here. Isolated CMOS. For isolated CMOS, we add an extra deep N well in the already existing NMOS and PMOS combination. We did this for better isolation and high energy ion implementation. BJT, bipolar junction transistor. So bipolar junction transistor basically works like this. So there are three regions: an emitter region, a base region, and then there is this collector region. So the emitter is highly doped. The collector is lightly doped, and the base is moderately doped. And there can be two type of BJTs. The picture shows the NPN BJT. There can also be PNP BJT. How does this work? So we are only talking about the active state of the BJT. So in the active state, the the base and emitter junction is actually connected in forward bias. So because of the forward bias, there will be electron flow from the emitter to the from the emitter to the base. There will be an electron flow, and there will be also a flow of hole from the base to the emitter. But the electron flow is much more major because emitter is highly doped, as you can remember. And also the base has a really low width compared to the emitter. And then the collector and the base is connected in reverse bias. So because of that, most of the electrons that have flown from emitter to the base will actually go on to flow all the way to the collector. So this will actually create a current flow from the collector to the emitter, because the current flow is basically opposite. Then we're gonna talk about DMOS. DMOS is basically this. The D stands for double diffuse. The double diffusion means the N plus source and P body diffusions. So here the channel length is fixed, only the width can be scalable. It is asymmetrical, so you cannot really change the source and drain. Remember, in the NMOS or CMOS, we could change the source and drain, and this is really highly effective bipolar parasitic. And so there is a drift region over here, which is a lightly doped region between the channel and the drain. And there is a deep N well, so that that provides an isolation between the substrate and the source or body. And we can actually combine these three to get our BCD technology. Thank you. That's the end of the slides.
Okay, thank you. Can you go to slide 11?
Oh, sorry. Yeah, sure. Slide 11, right? This one?
Can you share screen again?
I'm sharing screen. Can you see it?
So, do you know the difference between P substrate and P well? How different?
The P well is more P doped, like moderately P doped. The P substrate is lightly P doped.
How about P in body, P plus?
P plus is highly P doped, like highly doped with whole.
Highly doped.
Yeah.
And P well, how?
P well is moderate.
Moderate.
Yeah.
And P substrate
is light.
You mean P plus is the most dope, and P well is moderate, and P substrate is less light.
Yeah. Yeah.
Let's see. Next slide. Next. So what will happen if we have latch-up?
I'm sorry.
Latch-up bipolar characteristic latch-up.
Oh, actually, this part I am not really sure.
You're not sure?
Oh.
Actually, latch-up is an issue. So if you have latch-up, you can see this might break your MOSFET. It will have leakage current. Isn't it? Well, I'm not sure, but I just remember latch-up is an issue, right?
Yeah. So, so you talk about the BCD, right?
Mm-hmm.
So the difference between the BCD and the MOSFET is mostly because the BCD, they control the current, and the MOSFET, they are controlled by the voltage.
Mm-hmm.
So you can see the schematic on the low end you put there. So the latch-up happened when the VDD and there's suppose not any current flowing from VDD to ground, but for in some case, if you are biased the wrong thing,
Mhm.
so the latch-up current can happen from the VDD to ground, even though the MOSFET at the top here you turn off it completely, but because of the parasitic diode, no, not parasitic BCD, I'm sorry. So the
Mm.
current still flowing from the drain source of the CMOS to the ground. So
Mhm.
that could be happen. So that's why we call it a latch-up.
I see.
But why we have VDD and ground? Why VDD in upper figure? Why
Ask me.
VDD in shorts, right? Short is VDD. In the right side figure S shorts. VDD, you can see a register, right?
Mhm.
Register upper
This one.
upper figure, right?
Hmm.
Oh, yeah, right. Register connect to shorts.
Mhm.
That is VDD, right? Compare upper and lower figure.
Mhm.
Shorts is VDD, and then isn't it different, right? It body.
It's
It
not actually the body, but the
body
way
is
they draw
VDD.
is confusing, but I think they're the same.
Yeah. It should be VDD. Okay. Shorts. Is it in the same slide where the filter? Did you get it from the same slide in the PPT? Hello?
Yeah. What were you saying? Oh.
Yes. Maybe I will find out later. Okay.
Oh, so what do you want to?
I see your figure in the upper figure and lower figure circuit is not look similar.
No, I think no, they are the same because actually there's no bunk connection in the BJT. So the wire from the register to the BJT inside the end well, they actually going through. So you don't care about the connection of the bunk. So there's no bunk inside the BJT.
Roman source. I mean, when latch-up will happen?
So you can see that normally the way we see the parasitic BCD configuration is that they got the one P and N. So because two BCD is stacked together, so normally there should not be any current flowing through it because PN. So we have two diode connection. So normally there should not be any current flowing through it. But in some case, so it happened really short. So it's like a fail. They call it a fail trigger because so this happened when a really small current happened at the head of the BCD. So it's because of the also there's a resistor at your draw here, so that may make the gate of the BCD fluctuate a little bit. So it's not happen frequently, but in some case they did happen. So they will actually turn on the two PMOS accidentally, and then they will conduct a really high current flowing from the VDD to ground, but that happened for only really short time. But even for a short time, if we have a really high current flowing through it, so that might be a problem.
Short circuit, right?
Yeah. So actually, it's short circuit from VD to ground.
But I mean, what happened when it connection might happen. So when we connect wrong voltage into brain source and body, I mean the connection called latch-up.
Oh,
Maybe wrong layout.
I think this is for RAM. So
Yeah. So maybe
uh,
let answer in next meeting. So the
Ren,
connection for latch-up.
Yeah.
Ren, can I ask you one question? So did you ever study any subject about the structure of the BZT or the CMOS?
CMOS, I'm taking electronic circuits this semester, so I will study this semester.
But is this about the semiconductor devices?
Electronic circuits.
But
Can you share your table
Course syllabus?
Course.
Course schedule or syllabus?
The syllabus is fine.
Syllabus.
Just give me a minute then.
Yeah, so I just wondering.
I'm stopping the share, the screen share.
Yeah. So I'm asking because they are slightly different between the physical structure of the semiconductor and then how you study the circuit. So they are two different subjects. So I need to ask.
A minute. Okay, let me share my screen again. You see it, right?
Yeah.
Okay, I think
you are studying diode, finesse diode.
Yeah, right now I'm here. So diode models and circuits.
so you know about PN junction and everything, right?
Yeah.
Okay.
I also studied the like bipolar transistor like by myself a bit.
Maybe in week 9, physics of most transistor will have latch-up issues. Maybe.
No. So the latch-up only happen on the CMOS. So if they are studying about normal MOS and NMOS and PMOS, so I think they won't mention anything about the latch-up. But for now, I think the latch-up is not necessary.
Yeah. Okay. Actually,
Yeah.
in layout, some rules to avoid latch-up, right?
Yeah, right.
You are beyond the point of redemption.
Okay.
I'm sorry for the noise.
So today you only mentioned about almost physics, right? You don't know about electrical characteristics of the devices.
Okay.
I'm right now the diode mode, but
Well, take it easy. He's undergraduate.
Can I share
Ryan, can
screen?
you
like
back to the slide?
yeah, sure.
Yeah.
Wait. Yeah, can you see it?
Not right now.
Okay. Let me just yeah, you can see it now, right?
Yeah.
Okay.
So the BCD process is so far you only study the BCD at most. So the BCD process they have two different parts, two other things. So it's the CMOS and then the DMOS. I think you haven't studied it yet, so it's quite hard. So how much do you know about the normal MOSFET?
Actually, like in order to make these slides, I studied a bit about NMOS, PMOS, and then CMOS.
Right.
So these parts I actually studied all by myself, like just to make the slides.
Yeah. It's quite hard, I must say.
Now he only know about the physics, not electrical characteristic. That
Yeah, but I didn't know anything because before making these slides. Now at least I know
yeah.
like how things work a bit.
Oh, I
Yeah.
think it's better for both Ryan and Tick to start with the lecture from Professor Razavi. It's better to know the thing.
Actually, we are studying Rajavi's book right now.
Yeah, but I think you must go ahead a little bit.
I see.
Right.
Okay.
So
I asked him to study in advance because he cannot wait until the end of the course.
Yeah.
It's too.
Yeah.
mean,
That's true.
yeah, it would be hard, but sorry.
Yeah,
But-
don't worry about that.
But when you both study and use Cadence to simulate, you can better understand.
So
Instead of just
how do I find Rajavi's lectures?
So he had a free course on YouTube if you search for it.
Okay.
So he recorded and puts online, and also for the book, also you can find on the internet, I think. Yeah, Razavi Electronics 1 and
This one?
Electronic 2. Yeah.
There are charge carriers, doping graph. Yeah, this one, right? Okay.
So actually, he covers the content in his book, but yeah, it's slightly different. I mean, the real-time lecture is always different. So if you have time, you can watch it, but no, you study the book is just fine.
Okay.
Can
Yeah.
I see your lecture electronic
Circuits syllabus.
lecture?
This one.
Yeah. Did he put on your lecture?
The lecture
Or
books, I mean,
he only
Lecture.
post every week, or he did professor put on the lectures for this semester?
The lecture notes.
the
Yes,
material.
lecture notes.
and
Right. Lecture
Oh,
notes
lecture notes. Okay.
in week 9.
Week 9.
Yeah. CMOS.
Actually, he posts the lecture notes week by week, so I only have the first
Ah,
2 lecture notes.
I see.
yeah, no problem.
Maybe after this meeting, I will find some lecture note about CMOS for you to study first, right?
Okay, I think that's
Mhm.
good. But take it easy. Take it easy.
Thank you.
Can I send?
So
Yeah.
no. Can I ask one question?
Yeah, sure.
Yeah. So do you know the different? I know. I mean, the most important thing about the BCD process. Do you know it? So what is the difference between the BCD process and the normal CMOS process?
Um, the BCD process, like because there are like different because there are different like mechanisms in the same place, like you can take advantage of each of them.
So
Is
that's the hint. So what is the difference in their name? So the BCD, the CMOS, and the DMOS. So do you think what is the most important thing in this one in among those three?
among those three, which one is the most important?
Yeah,
I think it should be the CMOS.
second guess.
Then it's DMOS.
Yeah, the DMOS. So the CMOS, there's no difference between a normal CMOS and then a single NMOS and PMOS. They just put them together, so there's no difference between them. But the DMOS is the most significant thing inside the BCD. That's why we call it. So can you back to the slide with the DMOS?
Yeah, sure.
Yeah.
Here.
Yeah, so you can see here, so for the normal MOSFETs, so they are symmetrical, but for the DMOS, they are asymmetrical. So source and drain, they are different. So in the case, you can see that source and bungers, they are tied together, but in the normal NMOS, they are separate. And then you can see that source and bung and then the drain, their doping is also different. Can you see that? And also the way they draw the gate is also different.
Yeah.
You see, that's right. So I think you better take a look at why it's different.
Okay.
Yeah. I can answer it now, but it's no fun. So
Okay.
okay, I think that's one. So take a look at the DMOS.
All right.
Is there anything else in this meeting?
Are you asking him? No, I will share screen and explain Oh. Can you see my screen?
I think, Ryan, you had to stop earlier.
Yeah.
Okay.
Actually, you can see this from you cannot, if you accept to the server now.
Oh, the server settings. So I went to almost the last step. In the
Can
la-
you share your screen?
Yeah, sure. So wait.
How did you get the IP?
From
Uh,
Yi Dong Win.
Don't do nhầm. Okay.
just wait a minute. It's too long. Oh, sorry. All right. So now I have to connect to the. In fact, this is the stage. What's the command? Okay, now I should do this. And then I see 6. And then I see. Oh. But here the problem actually occurs. And now if I do what Hung said to me, the user
Oh. Right.
term, sorry. DMOS. Okay. Then I should put this thing. Then this message is shown.
Okay, I see. So actually,
One
we are not quoting from the MacBook, so
Right,
it's quite different.
because I open on window and no
I actually tried to install a VM and like try to use Windows from there, but that was quite a failure.
failure. Why?
Various reasons, like apparently you cannot use that for free.
Mm,
One, you know how to write VM, right? You are
Yeah.
using
what?
VM.
VMware? You mean?
You mean the
Yeah, it also, so I got an already set up VM with the Cadence and then Virtuoso everything. But it's quite heavy. So I don't know how to say it. Hmm.
How about in not not
Ryan, can you try this? I put it in the chat in the message.
I actually typed the exact same thing here.
Yeah, the same thing.
it's like if I were
User finish the LS display.
we are trying to open your file name display, right?
Mhm.
It's already exist, but why we cannot open?
By the way, like we have only 1 minute and 30 seconds left. So should we rejoin?
Sorry.
Like we have like 1 minute left for the meeting.
All right, I see.
Like should we rejoin or?
I will open the link again.
Okay.